Hello, and welcome to Thermochemistry Calorimetry applied to phase changes and heating curves. So, this is sort of the first step introduction to calorimetry. And the things that you will need for this are your 5A notes, and you can follow along with me. You may also want a calculator to do the calculations with me. And as in many of my casts, I would recommend pausing and trying the problems for yourself. And then you can go back and check your answers, or if you don't know what you're doing, watch and do them along with me. So, from our previous videos, we know that when something gains heat energy, it had to gain it from somewhere. Heat is always a transfer. So, that means that something else must have lost or produced that energy, and it's always going to be a transfer. Temperature is a direct measurement, heat is always a transfer, it's always a delta. So, whenever a substance or material changes in temperature, that heat can be measured by measuring the change in temperature. Not always is it true that things can gain or lose heat, and they don't always have to lose or gain in temperature. They don't always have to raise or decrease. That extra heat energy can go into other things like breaking IMFs or breaking bonds or things like that. So it's not always going to have a temperature change. But when you do have a temperature change, we can use the principle of calorimetry. That's a method of measuring the heat exchange. So we see up here. Calorimetry is a way of measuring heat exchange. And we can do this in experiments, or we can just use our calculations to measure it. So if we look at this equation, we have here Q. So Q it basically means the same thing as delta H. They're both measurements of heat or enthalpy. M is mass in grams, and there is a version of MCAT that's called NCAT, and that would be in moles, but the most common form of this equation is with mass. C is the specific heat capacity, and we're going to talk about that in 1 second because that's a very important number, not just to our calculations. And anytime we see a delta here, delta T, that means the change in temperature. So C final minus C initial. Okay, so we're going to come back and we're going to take a look, a more in-depth look at the specific heat capacity. You see down here. Okay, so specific heat capacity, and that's also up here. And the reason why specific heat capacity is important is sometimes you're not asked to solve for Q. You're just asked a question about a substance. And what we know is for specific heat capacity, good heat conductors like metals are going to have lower specific heat capacities. And the reason for that is that specific heat capacity is the amount of energy required to raise 1 gram of the substance 1 degree Celsius. Well, if you have really good conductors, it doesn't take much energy because they're easy to increase the temperature. It's really easy to heat up. So things like metals are going to be good conductors and they're going to have very low specific heats. The higher the per gram, the higher the specific heat capacity, that's going to tell you that it's a better insulator. So things that don't conduct heat as well. And so that value can tell us a lot about the substance. So you could connect it to something like intermolecular forces and what type of IMF is there and how does that compare to categorizing substances and such. Because the units for specific heat, if we look up here, the units are joules per gram degree Celsius. When you get an answer, the answer will always be in joules. If you want to make it kilojoules, you'll have to divide by 1,000. And they'll often ask for it in kilojoules, so don't forget that step. And make sure to label any of your answers with appropriate units, and those are all listed up here. Okay, so the last thing to consider with this is that you have to make sure that you check your sign. Because oftentimes what happens is when you're doing T final minus T initial, you accidentally will put in T initial and T final, but you should be able to use logic to figure out whether your delta H or your Q value should be positive or negative based on the circumstance. So something that is exothermic should have a negative. Something that's endothermic should have a positive. And I want to talk about that a little bit with phase changes quickly. This isn't in your notes, but just to relate back to this. So let's say that you have some water and it is liquid water. And let's say that your initial temperature is 23 degrees Celsius, so about the temperature of our classroom. Then let's say you do some sort of reaction. You mix something in and it reacts, and your TF is, let's say, 50 degrees Celsius. So because this had an increase in temperature, so this is the logic that we use. Because there's an increase in temperature, that means that this would be considered endothermic, and we should get a positive Q value or a positive delta H for this. Okay, so when the temperature changes, it's pretty easy. If you have an increase in temperature, it means that it absorbed heat energy. So this absorbed. If it absorbed heat energy, that means it's endothermic, and that means you get a positive Q and a or positive delta H. These two values, they mean the same thing for our purposes. So if you had, let's say, for example, water. So I'll do it again, water, and it's a liquid, and it started at T initial at 23 degrees Celsius again, but this time you put something in it, or um, you put it in a different location or whatever the situation is, and you measure the water with the thermometer, and your temperature comes out as 10 degrees Celsius. In this case, it has decreased in temperature. And if it has decreased, that tells us that it has lost heat energy. It's given it away. And what that means is that this would be exothermic because it has lost heat energy. And so that would mean that this would have a negative Q value or negative delta H value. So before you ever do your calculations in MCAT, you should already have figured out the logic of your sign so you can catch any mistakes that you may have made. And that's very important to set up because you often get a grade for the sign, for your units, and for the actual value for plugging in the correct numbers. So one of these problems in calorimetry could be, worth up to 3 points just for one section. Not always, but sometimes. Now let's look at a few different cases here with phase changes. And these are water. The subscript here is really low. So you have H2O liquid going to H2O solid. So this would basically be categorized as freezing, solidification. So this is basically creating ice. So we're freezing water. And so when we're figuring out whether this is endo or exothermic, I always say, well, let's try to put delta in. So what would happen if we tried to put delta on the reactant side? We add heat energy. Well, if you added heat energy, would liquid ever become a solid? Would it ever turn into this would be ice, right? Does that make any logical sense? No. So if you're not going to put it on the reactant side, it has to go onto the product side. And if it goes onto the product side, that means that this is exothermic. Sometimes people say, well, wait a minute, ice is cold. But you have to remember that hot and cold cannot really be used for phase changes. You have to use the logic of it. Okay. So, temperature changes alone. In truth, this never changes temperature. This stays 0 degrees Celsius through the entire process. And so you have to think about it in terms of whether heat is being lost or heat is being gained. So if heat is being lost, it's exothermic, which means you will have a negative delta H. All right, so if we come down here to the next one, we have H2O solid. So this is ice turning into liquid. So this would be the process of melting. All right, well, if this is melting, we can think about it by first trying it on the reactant side. If I add heat energy, will it make ice melt? Yes. You need heat energy to make it melt. That could be your hand, that could be from the room, that could be from wherever it's sitting on, okay? But you do need some sort of heat energy in order to make it melt. It could come from just the air around it. So because heat is being added, that is endothermic and is a positive delta H. Figuring out the signs before you do any calculations is very important. By the way, this also would happen at 0 degrees Celsius because those would be on the same line in a heating curve. So these are examples of phase changes. And there's a reason why we're not going to be able to use MCAT for this. We'll have to use something different. And that's because in order to be able to use MCAT, um, you have to have a temperature change. Well, in these cases, there's no temperature changes. So we'll have a way to solve them. But we're going to go ahead and practice some MCAT calculations before we move on to actually applying it to the heating curves. Okay, so this problem says that we have aluminum metals, we're assuming that's a solid, has a specific heat of zero 0.9 joules per gram degree Celsius. How much heat is required to raise the temperature of 6 gram sample from 20 degrees to 80 degrees? All right, so because we have a temperature change, we can use Q equals MCAT. So we're going to start it out. Q equals MCAT. Always a good idea to write your equation out first so you have a guide to follow as you plug in your numbers. We want to solve for Q in this case. You don't always have to solve for Q. The mass of this is going to be 6 because it's a 6-gram sample. C is the specific heat. That's a constant that's given to us. You can also solve for that if you were to know a Q. And then the temperature change. So we need to do T final minus T initial. So T final is going to be 80 because that's what it is in the end, minus 20. And at the end, we're going to go back and make sure we do a quick check for this to make sure that we have the right sign. So now it's a matter of plugging it into your calculator. Be very careful to subtract this as 60 before you put it into the calculator or leave the parentheses around it. All right, and so your final answer should be 324 joules or 0.34 kilojoules. I just divided by 1,000 if it wants it in kilojoules. These are not kilojoules per mole because 6 grams of aluminum isn't equal to 1 mole. So these are this specific example. So it's not an intrinsic property. This is in this exact example, how much did you release? And let's go back and make sure that we like our sign. So we went from 20 degrees to 80 degrees. That means we increase in temperature, which means we absorbed heat energy. So this would be endothermic. And if it's endothermic, you should have a positive Q or a positive delta H value, and we got a positive value. And I always think it's a good idea to actually just go back in and actually put the sign as a double check that you got what you intended to get. All right, let's do the next problem. In this problem, it says how much heat is released. That's a good keyword to kind of highlight right there, released, okay? When a 2-gram piece of aluminum is cooled from 300 to 25 degrees Celsius. And we're assuming there's no phase change in here and then we're under the melting point, so it remains a solid the entire time. So again, we're going to be able to use Q equals MC delta T. One of the big differences for this one is we should expect to get a negative Q value because heat energy is being released. That means that this should be exothermic. It's giving off heat energy. It's giving up its heat energy. And we see that because that's what's causing its drop in temperature. All right, so for this one, we've got Q equals, the mass is 2 grams. The specific heat from the page before is a constant, so we can still use that. And the change in temperature is 25 minus 300, and that's what actually gives us the negative value when we subtract. And always remember, when you put this into the calculator, either subtract this before you put it in the calculator or don't forget the parentheses here and here. So we'll put this in the calculator. So the specific heat of water is 4.18 joules per gram degree Celsius. If you put 850 joules of energy into 40 mils of water, initially at 23 degrees Celsius, what will be the final temperature of the water? Okay, so in this case, we're not solving for Q, we're given Q. So here we are given the Q value. And we also have to be a little bit careful here because we don't have a mass, but if we remember with water, anytime you have milliliters, you can convert it to grams because the density of water, if it's pure distilled water, is 1 gram per milliliter. So 40 milliliters would be 40 grams. So now we're going to go ahead and write out our equation. So we have Q equals MCAT. Q is going to be 850. Make sure it's in joules before you plug it into the equation because it can't be in kilojoules. Our mass is 40. And just to double check the sign, it says you put 850 joules in. That means that this is endothermic and that the value makes sense being positive. The specific heat for water was given to us is 4.18. And our change in temperature, it wants the final temperature, so we don't know that. So that's TF, and then minus 23 degrees C, because that's the initial temperature. It's always a delta, a change. So probably the best way in terms of algebraically solving this is to go ahead and multiply these two numbers together and get one value. So we get 167.2 equals 850, and this is still going to be TF minus 23. We haven't done anything with this. Let's go ahead and divide both sides by 167.2. Okay, these two cancel out. 50 divided by answer. So this is going to give us 5.08 equals TF minus 23. And then to both sides, we can just add 23. And we end up getting T final equals 28.1 degrees Celsius. And let's go back and make sure that makes sense. If we put heat energy into it, should the temperature increase? Yes. All right, how much heat is required to raise the temperature of 10.5 grams of ice from negative 12 degrees Celsius to 0? And we notice here that the specific heat for ice is different than water, and that's true that every different state of matter for a substance will have a different specific heat. They're not all the same because they have different thermal conductivities. All right, so we will solve this one, and we're trying to solve for Q in this case because we're asking how much heat equals MC delta T. And so Q equals mass is 10.5. Specific heat is 2.06. And the final is 0 minus a negative 12, so that would be plus 12. So the reason why that changes to plus is because that's a negative sign. And again, we're going to go back and make sure that our sign in the end is correct because that's very important. Okay? And so when we multiply these all together, it's equal to okay, so we end up getting 260 joules or 0.26 kilojoules. And these would be positive because you're adding heat energy in. That's how you're increasing the temperature from negative 12 up to 0. And so that would be a endothermic process of increasing the temperature because you have to put heat energy into it required. The next video will pick up where this one left off. There will be a part 2 where we'll look at how we can apply this to the heating curve.